right, so we are going to pick up where we left off. So we are in the midst of creating accumulation functions given rate of change functions, okay? And so the process that we go through in order to do that is to start with an exact rate of change function and create an approximate rate of change function. And so the process by which we've been doing that is to first partition the x-axis and then reassign x values in a given interval to the x value at the left end of that interval. And choosing the left end has been an arbitrary choice. We could have chosen some other point within the interval, but this is for convenience, okay? It's easier to visualize and talk about this way, okay? So you had homework that wanted to get at making sure you actually understood this part of the function. So I've got a few questions about it, so I just want to make sure that we're all on the same page. So let's take a look at that really fast, okay? So number one of your homework was making sure you understand the left, mid, and right functions. What are the inputs of these functions? What do we put in? Current x value. What does the mid-x output? Do I need my Anthony? The midpoint of which interval? The delta x interval? Any delta x interval? The first delta x interval? The last delta? The one containing the current x value, okay? So if I've got, as I do in this scenario, a is 1 and delta x is 2, I could imagine drawing a number line, right? So I'll start 0, 1, 2. Okay, so I start my partition at 1, and then my intervals have length 2. So from 1 to 3 is one interval. And then from 3 to 5 is the next interval. And from 5 to 7 is the next interval. Okay, so when I plug in 1.5, that's here, it's going to output what? Oh, sorry. Let's say left of x will output what? 1. When I input 2.999, that's right here, right? What's that going to output? I heard somebody say 2, and I heard other people say 1. This whole interval is length 2, so the left endpoint of the current interval is 1. Okay, so it'll still output 1. What about at 4.1? So that's over here, 4.1. What's the left endpoint of that interval containing 4.1? 3. So that will be the output of left of x. Okay. Is that okay? People got that? We're good here? Okay, good. Because if that doesn't make sense, then a lot of things don't make sense. So, all right. So then after that, the whole point of doing that was so that we could define a step function, okay, as a piecewise constant rate of change function, okay, where the value in each interval is the actual rate at the value that we found in the previous step, okay? So that was the last page of last Friday's assignment, okay? So let's take a quick look at that, okay? I posted solutions to the first 3 pages. I hope you took time to look at those. But here is a sample of what this looks like. So the blue line is our exact rate of change function. Notice it's a changing rate of change function. Okay? When you look at different values of x, you get different values for the rate of change. Okay? So what I've done is I have created an approximate rate of change function, okay, by choosing a place to start partitioning the x-axis and choosing interval widths and then assigning values of my approximate rate of change function to the left, by using the left endpoint value of the actual rate of change function, okay? So I decided to start at a equals 0, So I've got, a delta x interval of 1 here, and then delta x interval of 1, delta x interval of 1, and I'm using the left endpoints, okay? So how would I represent the exact rate of change at the left endpoint of the fourth interval? So let's say that this is, I think it had a name, but I'm going to call it r of x for now, okay? So let's say that's r of x. And this is going to be our approximate rate of change function, which we'll call step of x. Okay. So how do I represent the exact rate of change? David Q? Need some help? McLean? Corresponding y value of that point. Okay, so here is my fourth interval. The left endpoint is, here, okay? And so I can figure out that y value by doing what? I know what the x value is, right? It's r of 3. Because I've made the choices to start my partition of the x-axis at 0, and delta x is 1, okay? So r of 3 is the exact rate of change at the left endpoint of the fourth interval, okay? So if I have a current x value of 3.3, okay, so I'm here, what is the approximate rate of change at this x value? Jan? Are you here? R of 3. How'd you figure that out? Right. So every x value in this interval takes on the same rate value that's at the left end of the interval, right? So this is also r of 3. And if I let x be 3.65 or 3.99998, right, then it's still the same r value. And that's the point. We're trying to create an approximate rate of change function that's constant within a given interval, okay? So how would we actually define our approximate rate of change function for the fourth interval? Yes, oh, question? Uh-huh. So you're thinking about ways we could improve our approximations, and those ideas are perfectly valid. But the thing is, I've already made choices. So I've already made the choice to use left endpoints and to use delta x equal to 1. Now, in order to do what you're saying and improve my approximations, I could redefine step of x to use the right endpoints or the midpoints and let delta x be 0.5 instead of 1. And those would be ways to improve. But once we've made those choices, we stick with them the whole way through. That's a really good question, okay? So in fact, yes?
For an answer in part C, you gave the approximate y value.
Okay.
Is that acceptable?
I think it's 9. Yeah. For part C, it is. For part A, it's not, because I asked you to represent it. Okay? All right, so how do we define the approximate rate of change function for the fourth interval? So I'm calling my approximate rate of change function step of x. So what I'm looking for is what is the definition for step of x. So if step is the name, x is the input, step of x is the output, and what rule do I write on the right-hand side to define this function? Arian? R of left of x, right? Because again, what does this approximate rate of change function do? It takes in a current x value, it reassigns it to the left endpoint, and then it spits out the rate of change at that endpoint. Okay? So this is composition of functions, right? You read inside out. Okay? Is that cool? No, not cool.
It's not done.
Oh, what am I missing?
You want to define it for the fourth interval.
For the fourth interval. So that is when x is between what and what?
3.001.
How about 3?
No, because that falls back onto 2.
Does it? So if I put left, so if I try to evaluate what is left of 3. Yeah? Never mind. Okay, what are you guys debating between? What are our choices? Uh-huh.
So I think we were reading about whether 3 is less than or equal to x, and then less than 4, or is it 3 less than x greater or
Mm-hmm.
less than or equal to 4?
Mm-hmm. Yeah? Mm-hmm.
That's what our step function is. I mean, if you were doing right of x, then it would probably be 3 is less than x is less than or equal to 4. If we were doing, but we're dealing with like the left, so we want that left point included in each one, so we have to include the 3.
Great. So worst case scenario, you go back to the definition. The definition of left was a plus the floor of current x value minus a divided by the change in x, right, times the change in x. So what is 3 minus 0 divided by 1? 3. What's floor of 3? 3. So this does, in fact, output 3. Okay? You don't have to work that hard because you already did. You have the rule. You can figure this out. Okay? Don't forget what you already know. We worked hard for this. Yes?
If we did right of x, would we have the less than or equal to on the right side then? If we were concerned about the right?
Mm-hmm. Yeah. Okay. Cool. So, okay. So that's what it is for the fourth interval. Okay. But if I want it in general, right, how do we define our approximate rate of change for all time? Do I have to work that hard? So now I want my approximate rate of change function for all time between 0 and 4. So if I put in an x value, what happens to it? Rashay?
It's going to be rate of left of x if 0 is less than x is less than 0.
Well, we can go ahead and say up to 4. Okay. That's it. Notice I don't have to create a piecewise defined function because it's already encapsulated by doing this left of x thing. Okay? So I don't have to define piecewise functions. It's already automatically done because of our definition of left of x. Okay? Now, doing it this way gives us this calculator drool thing that I keep talking about. Oh, question?
So for that one, why isn't x is greater than or equal to 0 and less than or equal to 4?
Oh, that's just because I wanted to,
Is it because it's all the time between 0 and 4?
yeah. It's because of the English sentence.
So it's just like including 0 and 4.
Yeah. Okay, so the thing now that I want to talk about really fast, because it was driving me nuts and I figured it out. So how do I make this calculator drool disappear? I don't like those. They're ugly. So, and I'm sure you guys saw them when you were doing your homework and it's like, ugh. So how do we make it go away? Well, those are vertical lines that appear where? At the left endpoints, right? So if I don't want to see those, then when I tell graphing calculator to graph my step function, right? This is what I have to type in to make it graph it, okay? But if I don't want the calculator drool at the left endpoints, right, at the breakpoints, then I say, as long as x is not equal to a left endpoint. And if I tell it not to graph there, then it's not going to graph there. So there will be no more vertical lines. Okay? Right? Remember, graphing calculator does exactly what you want it to do. You just have to tell it. Okay? Now, you might be wondering how you get the not equals. On a Mac, it's option and then the equal sign. I'm not sure what it is on a PC. Control Shift N, maybe? Okay. We can play with it, and it might be on this sheet, I think. Okay. So how does that feel? Pretty good? So that was your homework. I'm not going to post solutions because I just did it. Okay, so you can rewatch the video. Now, so that you have an idea, because I feel like maybe the motivation is being lost a little bit. We're working so super hard. So I want to remind you guys why we're working this hard. Okay, we're creating this notation so that we don't have to do it by hand. Okay, if I want to create accumulation functions, I'm doing an awful lot of work and still not getting very good approximations. So at the end of the day, our goal is to have the computer do it for us. So if I have my exact rate of change function, I have my delta x, which I defined to be a slider, okay, which means I can let its values change. Okay, so at the moment, the value of delta x is 2. Okay, and so I've graphed the exact rate of change function, and I've created an approximate rate of change function using left of x with the starting value at -1 and delta x equal to 2. Okay, is everybody comfortable with what we're seeing right now? Okay, but as we've talked about, right, this is not a very good approximation. I want to make it better. And the way we've talked about making it better is by letting delta x get smaller. And so notice as I let delta x get smaller, my approximations get better and better. What exactly do I mean when I say my approximations get better and better? I mean that I get closer to the actual value. Exactly. Beautiful. Okay, so, I have to zoom in, right? I have to zoom in really far, and then I start to see the difference. But if I keep making delta x even smaller, that difference keeps getting negligible, right? That's where we're going, okay? And I did all of that just by sliding my cursor on a computer. It's beautiful, okay? So that's where we're headed. That's what all of this work is about, okay? So let's keep going. Okay, so what we have now accomplished is to define step of x, which is what we're calling our approximate rate of change function, by using an exact rate of change function, okay? So that's why whenever I graph these things, I always include, like the blue graph is the actual rate of change, so that you can see how our approximate rate of change graph compares, okay? Now, the whole point in doing this, okay, The whole point in creating an approximate rate of change function was so that we could use our previous ideas about like little bits of change to talk about accumulation. Okay, so if I have a constant rate of change, I can compute like little bits of accumulation. Okay, so in this picture, I've got some things going on. Okay, and so we talked about this a little bit like 2 lessons ago. Okay, so in this picture, I've got a blue graph, which is my exact rate of change. I've got my purple graph, which is my step of x, which is my approximate rate of change. Okay, so sorry, I didn't have time to delete all of these. Okay, so so we've talked about 1 through 5 already. Okay. It is time to move on. Okay, so let's pick up at number 6. Okay, so I want to relate what we're seeing in the graph to the sum that's written beneath the graph. Okay, so relate the sum. What does each part represent? What does the whole sum represent? Take a minute, talk to your neighbor, and we'll regroup. Okay. All right, Moises, you got some ideas?
Yeah, well, what I kind of figured, I don't really know. Each part represents a step.
Each part, like this whole thing?
Yeah.
Rep-
Assuming, and then the sum is the whole function put together.
Okay. Jonathan Russo, do you have? I'm intrigued by this wording. What is the sum of a graph? Okay. Are you talking about this sum and then this graph separately, or because I'm hearing the phrase sum of the graph, and that doesn't make sense in my brain. So I'm trying to figure out what you mean. Vishay, do you have, or were you stretching?
No.
Okay.
I'm not exactly sure how to word it properly, but if the blue line / pink lines are, say, feet per second,
Mm-hmm.
and the x-axis is seconds,
Okay.
then the sum at the bottom of the graph represents the accumulation of little bits of change in the feet.
Ah. Okay. So maybe assigning some units will give us a way to talk about this. Okay. So let's say, I like it. We'll go with that. So this rate of change is giving us feet per second. The x-axis is seconds. So if I wanted to talk about what something of the form R1, so R1 is a rate. In fact, it's the first constant rate that we see in this picture. Okay, and R2, so this is R1. R2 is this, this y value. R3 is this y value. R4 is up here, this y value. Okay, so those are rates, and we're multiplying them by little bits of change in x, little bits of change in time. So collectively, I could think of this quantity as a change in y, right? It's a little bit of accumulation. So if this is feet per second and the x-axis is in seconds, then a little change in y is going to correspond to a change in what? What's the units on this? Is it seconds? Feet per second? Feet? If I do a rate times a little bit of change in time, this is going to be a change in feet. This is a little bit of accumulated distance traveled. Is that, yeah? Okay, and so then this would be another little bit of accumulated distance, another little bit. Okay, so we've got all of these little bits of changes, right, corresponding to each of the terms. Question?
Exact or approximate?
Ah, excellent question. So you guys tell me, are these exact or are they approximate? Yay, music to my ears. These are approximate. Why are they approximate? Because we made it that way, right? Because we're using the constant rates from our step function, okay? So these are approximate little bits of changes in distance, okay? So when we add them all up, now we're talking about an accumulated change in distance, right? Okay. All right, so what above shows the accumulation from x equals 0 to 1.2? So let's, just in case you're far away and you can't see, so I started my partition of my x-axis at 0, and I chose my delta x to be 0.3, and I'm using the left endpoints. So that's how I created my step of x function, okay? And now I want to talk about the accumulation from x equals 0 to 1.2. How would I do that? So of course, where this is the approximate accumulation. Maybe I should back up. I said very loosely that this whole sum from the first term through the 10th term was an accumulation, right, of distances traveled by taking little bits of changes in distance. But how far did that actually take me? Like, I've got 10 of them. Delta x is 0.3. So I've gone through 3 seconds, right? It's all, this sum is representing the accumulated distance for the first 3 seconds. Mm-hmm. Okay, so now we're moving forward. So now if we want to talk about from x equals 0 to 1.2, okay, well then I would want the little bit of accumulated distance or change in distance here, plus this change in distance, plus this change in distance, plus the change in distance from here, right? So I'd want the first 4 terms. How would I write that using summation notation? So we're going to start our sum at I equals 1. We need 4 of them. R sub I, delta x, okay? We could also call those changes in y sub I, right? to really get at the fact that we're looking at little bits of changes in distance. Yes.
How do I differentiate? One of the things that's a little confusing is differing in my equation for telling it, am I using my summation notation to measure across an interval or an actual point?
Like what the I is standing for?
Yeah.
So the I is representing just which term. It's your increment to say go from the first to the second to the third to the fourth term. Now it might actually help you represent something when you create your equation. So in this case, the y sub I is telling you, oh, this is referring to the second change in distance or the third change in distance. Okay, we're gonna have some more practice.
So the I is where, like, because it goes from the 7th and it goes from 1 to 3.
Yep.
The I has nothing to do with what your delta x is when you split up.
Nope, I does not determine delta x. No, that's a good question. Okay. All right, so what would show the accumulation from 0 to 2.2? You want to talk to a neighbor, figure it out? Or do you feel like you can answer? So 2.2 is right here. Ruby? Are you here? Yeah? Where? Who am I looking at? Ruby? Hi. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Does it cover the entire interval? Okay, so this was a little bit trickier, right? Taylor Shackelford, did you have a way to address this?
I was gonna say it's like R1 delta x
Mm-hmm.
through R7 delta x.
Okay, so I'll shorthand that.
Then plus R8 delta x point 1.
Delta x 0.1. So you're trying to encode that the change in x is not.
Yeah, it's not like the full value of Rx8 or of the R8 is only the 0.1.
Okay, so let's not use delta x then, since delta x is fixed at 0.3, and let's just call it for what it is. It is, 2.1, or sorry, 2.2 minus 2.1. That's the change in x for the current interval, right? So then the associated change in y for that little bit is going to be the current rate times that change in x. Okay? How is that? Kind of nifty, right? So, oh, I went too fast. Question?
I guess I didn't understand your wording when you said plus R8, and then in parentheses you put 2.1 minus.
2.2 minus 2.1. Yeah, I made a boo-boo, and then I tried to fix it. Question?
I was just wondering if it would be, like, if this was given on a test and we were to say if that was 1/3 of that interval, if you had just taken r sub 8 delta x and then times it by a third. It's like 1/3 r sub 8 delta x.
I mean, that is not wrong. It's just not as generalizable as what I wrote down. Okay, so and that's what we're about to do this for reals. Okay, so so let's do it. Okay, so what we're talking about right now is creating an accumulation function. So we're going to call it a of x. Okay, is the accumulation of the quantities starting from a and terminating at the current value of x. Okay, that's what we're setting out to do right now. Okay, so we've already talked about, so this is the same image as from before. So if I want to represent what a of 1.2 is, we already talked about how we might do that, right? It was this, you know, the sum of the r sub 1 delta x plus r sub 2 delta x, blah, blah, blah. Okay, so like this. Okay, now let's break this down though. Okay, so this is a nice representation of what a of 1.2 is. But what specifically are the rates? Well, that's what we worked so hard to do. Okay, that's what all of this creating an approximate rate of change function thing was about. Okay, so these are what? So what goes in the blanks here? So if we wanted to, like, not totally jump the gun, I could say, well, r sub 1 comes from finding r of, so this rate comes from taking r of what? So give me a specific number. 0, right? And then the second rate comes from taking r of what value? So remember, a is 0, delta x is 0.3. So this is r of 0.3. And this would be r of 0.6, right? And then 0.9, okay? But can I do better? Remember, the goal is to generalize, okay? So, so let's try to generalize, okay? So instead of writing 0, I could think of that as my starting value plus how many intervals? How many complete intervals? 0, right? And then 0.3 I could think of as my starting value plus how many complete delta x intervals? 1 delta x intervals. And 0.6 is my starting value plus how many intervals? 2. Do you see what I'm doing? Oh, I lost it. So 0.9 is the same as 0 plus 3 delta x intervals. Okay? Starting value plus how many intervals? Okay. Now, oh, whoops. I didn't have to erase. I had another line for that. Okay, sorry. So this is, everything I just wrote is what I meant to write here. Okay. Now, if I wanted to, again, the goal is generalize. So I've got specific values. 0 is my A, and so really I could say, you know, this is A plus 0 delta x, and A plus 1 delta x, right? A plus 2 delta x. Now my goal is to say all of this in summation notation. Okay, so this is adding up how many terms? 4 terms, right? So from 1 to 4, And each term is R of A plus, now here's the thing, I is 1, right? But this number, the 0, the 1, the 2, the 3, those are the things that are incrementing. Those are the things that are changing. But it's not equal to the I value. What is it in relation to the I value? 1 less. So I could do I minus 1 delta x. So that is the input of my R times the length of delta x. Okay? So far, so good? So this is done in term with J instead of I. Question? Mm-hmm. I will continue to be in increments in 1 unit chunks. Okay? The delta x is what you're thinking of changing. And so as soon as you say let delta x be 0.5, well, if I still want to get all the way, you know, to 1.2, that's going to change how many terms I need, right? I will always increment by 1. Okay? Delta x can change. Ahmed?
Why can't you start with I equals 0 instead?
You could.
And then like have the input as just I instead of I minus 1.
Right. You could make those adjustments. I'm choosing not to for the sake of consistency and keeping it simple. Okay? So one way is the way we're going to look at it. Okay? But what you're saying is valid. Okay? All right. So the A of 2.2, though, we talked about, is a little bit different in the sense that we've got 7 intervals of total, like, delta x length, okay? But then there's a little bit more, okay? And so how do we account for this? So we want the extra accumulation from part of the interval, and that comes from, so we have our first 7 terms, right? Our first 7 bits of accumulated distance, okay? But then we want to add a little bit more. And so that little bit more comes from doing the rate in the last interval times the change in x in that last interval. But the change in x here isn't the complete delta x. It's just a little bit of it because 2.2, right, doesn't cover the whole span. It's only that much of the 8th interval, okay? And so you could rewrite all of this, okay? So the rate in the 8th interval is R of 2.1, and the change in x in that last interval is 2.2 minus 2.1, okay? Okay, but these are still very specific numbers, and remember our goal is general. We want this to work for anything. If I change delta x, if I change a, I want it to still work. Okay, so 2.1 is the left endpoint of the interval containing 2.2, right? And so R of 8 or R of 2.1 could also be thought of as R of left of 2.2. Okay, and 2.2 minus 2.1, well, that 2.1 was the left endpoint of the current interval. So computing the change in x in the current interval can be done by taking the current value of x and subtracting off the leftmost endpoint of that interval. Okay? Do you see how we've just gotten way more general? Bless you. Okay. We can now do this for any delta x's, for any a's. Okay? So once again, okay, we're trying to create an accumulation function that will output the accumulation if we start at A and go to the current x value, okay? So starting at A, arriving at some current x value, that's where we're trying to accumulate to, okay? That is the left x value, okay, left of x, the x value at the left end of the current interval of x. So a of x is going to be the sum of bits from however many full delta x intervals you have, and add what most likely will be the case, a little bit more from the last partial delta x interval. Okay? And so we get the sum of the little bits, the sum of the bits from the full intervals by taking the rates at the left end of those intervals times the width of the full interval. And so we can summarize that this way. Now notice I haven't put in the top value here. Okay? So this number should be the number of complete delta x intervals. What was that again? We did that. How do you compute the number of complete delta x intervals between a and x? Jessica? You said it. Oh, no, that's not what I heard. The floor of x minus a over delta x, right? Because remember, x minus a over delta x is the relative size of x minus a to delta x, i.e. how many delta x's make up the measure of x minus a. Take the floor of that. That gives you the number of complete delta x intervals, okay? So this summation that I've got, this complete summation, is the sum of the bits of changes from the full delta x intervals, okay? And then to get the little bit more, we need the rate at the left end of the current interval times the change in the current interval. So this is our accumulation, folks. We did it. Okay. This was the journey. And now what we're going to end up doing, as I showed you at the beginning of class, right, is we're going to make this. So this is, so let's be careful. So this is an approximate accumulation function, right? Because we built it from our approximate rate of change function, okay? Right? Because we're doing all of these R of lefts. So these are approximate accumulations. And what we're going to do is we're going to make this accumulation function, this approximate accumulation function, really good. Again, the same way that we thought about making the delta x's small on our approximate rate of change function. Well, making delta x's small is going to have the corresponding effect of making this approximate accumulation function very good as well. Okay? That's where we're going. So, you'll have reading and homework for Wednesday. I'll post those hopefully by 1:30. And have a wonderful afternoon. I have office hours if you want to talk about anything.